So atomic structure has three parts. So the first part that we're going to look at is concerning the internal structure of an atom and some of the calculations that are necessary whenever we're dealing with the inside part of an atom. So part one, so there are three parts. So the first part is where we talk about electromagnetic radiation, EMR. So this is just called electromagnetic radiation, the effect of radiation to the subatomic particles of an atom. Then the second part is where we discuss periodicity, the trends of the periodic table, so periodicity. Then the last part is where we talk about chemical bonding. So this is one of the longest topics you ever have. So it will really take time for us to finish it, but according to our agenda, we should be done by before next week, because we're going to strictly follow our agenda. At least we should be even halfway through it. So we'll start with the part one. So part one is simply going to be referenced to what you discussed under biology. You remember you said an atom has what? Your atomic number, your mass number, you know all those things. You still record, right, the electronic configuration. If I give you this, you already know. This will give us what? You say 2, 8, and 1. And you know from your biology, we say the configuration now is going to be written as 1s, your 2s, your 2, 6. Then you have your what? You have your 3s1, right? So this is just prerequisite. So this is about an atom. You know this already from your biology. Now we're saying these subatomic particles, which is simply the protons, the neutrons, and the electrons that are found in the atom. The only one that give atoms their properties is simply electrons. Why? Because electrons are the only particles in an atom that are freely moving. So these are the guys that freely move. So these are always freely moving. They are always in motion. The other two are stuck. They are found in the nuclei or in the central part of your atom. So they are really not going to give any challenges when it comes to the properties of an atom, or rather an element. So in part one, we're going to look at what happens when we expose atoms to electromagnetic radiation. And there are so many theories that these guys came up with in terms of trying to discover the internal structure of an atom. And all their theories were based on hydrogens. Why? Because hydrogen only has one electron. So it was easy for them to observe hydrogen because the randomness was easy to be observed as the focus is only on one electron. Other atoms are a bit challenging because you have so many electrons, so it's hard to control all of them. So all the theories, so these are what are called postulations. So there are certain postulations that they made. So postulations are just like theories without proof, right? So theories without proof. So that's what we mean by postulations. So so we say theories. Let me just write them for you so that at least you know them, because they will do ask them under your tutorial sheet, your assignment. So the first thing that they came up with is that electrons give elements their chemical properties. So that's the first thing that they came up with. That's what you have. And of course, we discussed to say these are always in random motion. These are always moving. So there's always motion of electrons. So there is motion of electrons. That's the thing that you have. Then there are names that you'll be exposed to which is the common one that you're going to study, or rather to find in books, is the guy Rutherford. So Rutherford simply used hydrogen to explain all the properties that are found, or rather to explain the whole behavior of electrons, protons, and neutrons. Then after a certain period of time, this guy here, Boas, or Neo, this guy here, this guy came along, and then he just generalized all the principles that this guy came up with using a spectrum and everything else. So the main takeaway here that we're going to discuss under electromagnetic radiation, under the first part of atomic structure, is EMR. So we cannot study all this. This is just for your own information. So to start, what is important, we're just saying we cannot study electrons with our bare eyes. We have to expose them to some form of energy, and that energy is what we call electromagnetic radiation. That's where the EMR is coming in. So this guy here. So this is the first part. All the calculations and all the discussions we'll make will come from the behavior of electrons whenever they're exposed to what? To radiation. Because these theories had limits. These guys faced challenges because they didn't have enough equipment for them to pause and study the behavior of electrons. So all their assumptions were found out to be correct after a certain period of time, when these guys discovered that the correct media to expose an electron to, for us to pause it and also to allow it to move, to just be able to study it, is electromagnetic radiation. But this EMR made these electrons to behave as if they are wave-like properties or particles, and hence the certain things that we're going to experience. So it behaved. So this thing made electrons to behave like waves. So like from your physics, we're now going to say these things, first and foremost, the first thing we're going to discuss here is that these things actually have a wavelength. That's the first thing that we're going to say. So wavelength is going to be denoted by the letter lambda. So in case you didn't get what I said, guys, we're just saying we want to study the internal structure of an atom, and to do so we cannot look at the internal structure of an atom with our bare eyes. And the only environment where we are able to study the structure of or the behavior of an electron is when we expose that electron to electromagnetic radiation. But whenever that is done, the electron will start behaving as if it's a wave. It will have wave-like properties, meaning it's going to have wavelength, and this is measured in meters. So this is measured in meters or nanometers. So these are the two units that we're going to be using. So we're just saying, imagine this is your wave. So if this is your wave, so you learned here from physics in high school to say from point, if I say from this point up to this point, this gives you a complete wave, right? One whole complete wave. Or you can say from here up to there, or you can say from this point up to this point, right? This is simply going to give you this whole thing up to there. This is a single wavelength. So this is simply the length of one single complete cycle. This is simply what you're simply going to get. Yeah, so the total distance for one complete wave to be made, that's simply your wavelength. And this is always going to be related with frequency. So the other thing that we are going to also mention is frequency. So except here, frequency is going to be denoted by letter V, unless otherwise. In chemistry, under this topic, the letter V will be meaning frequency, and the units here this guy is measured in, the units for frequency is simply hertz, or we just say per second. Yeah, and this just means how how fast is the wave moving, like how frequent is it. So if I may illustrate this, if I show you something like this, it simply means this wave is very frequent as compared to when it's like this. So you notice here it was very frequent, right? And here it was not. So this is what frequency simply means. And these are the units that we're going to use to measure it. And the third thing is that these are always going to be having the same speed as light. So they move with the speed of light, which is simply c. It's a constant. C is simply 3.00 by 10 to the power 8 meters per second. Other people just say c is approximately the same thing as 2.998 then times 10 to the power 8 meters per second. So they will be specifying which one you need to use. Are you guys able to get me here? Macnon, you're getting what I'm saying here, right? So we're just saying these guys will have these properties, and apart from these three, before we even talk about anything else, the same reason, or rather the only reason why these electrons are always in a random motion is because they have energy. So that's another thing you can take note of. So these guys have energy for them to be able to move. So the whole idea of energy is to say these electrons can actually move from one particular shell to another, and this can be illustrated nicely. We'll talk about the type of series later on after we do the spectrum. So you have shell number 1, this is shell number 2, then we have shell number 3. So we're just saying an electron has the liberty to move from one particular energy level to another. So if an electron is here, it can actually jump and go to a higher energy level, or it can fall from a higher energy level then fall down to a lower energy level. Yeah, so this is basically what we are saying. We can have excitation. So electrons, since they need energy for them to move, if it has a higher energy, meaning it can actually lose some energy and then it falls down, or it can gain, if it's at a lower energy level in a lower shell, it can gain energy and then it's excited, it goes to a higher energy level. So the process of moving from low to high is endothermic, meaning it has gained. Then the process from dropping from a higher energy level to a lower energy level is exothermic, just the opposite. So now here we are saying we are having the following relation between the first guys that we discussed. So we're just going to say the equations so far that you need to know is that the three properties that we discussed, that was your frequency, your wavelength, and also your speed of light, your speed. These guys are connected. So what's the equation that connects these three? For those that have done this topic in class, what's the equation that connects these three? What's the equation, guys? What's the equation? So the equation is just that so V is equal to the speed of light over lambda. So this is where, of course, things haven't changed. Like I said, this is the only topic where V means frequency, not velocity, but frequency. Then C is the speed. This is the speed of light. It's a constant, always given to you. Then this is simply our wavelength, which is supposed to be in meters all the time. Yeah. So this is the first equation we ever learn under atomic structure, this guy. And there is a conversion you need to know when it comes to wavelength. Wavelength, we just say 1 meter. 1 meter is always equal to 10 to the power 9 nanometers, in case there's ever need for you to convert. Yeah, so if I may give you an illustration here, so if I may give us an example. So example, we're just saying find, So here they are saying what? They're saying the convergence, they're saying the convergence limit of a hydrogen atom is, so they've given us the number to be, let's say 342 nanometers. Find the frequency. So they've given us the wavelength, right? The wavelength has been given, though the wavelength has been given in nanometers. So we are looking for frequency. Frequency is equal to the speed of light over what? Over the wavelength. The speed of light is always given. It's 3.00 times 10 to the power 8 meters per second. Then we have to put this guy, but it has to be in meters. So meaning we just need to convert it. So if you convert this, 1 meter is equal to 10 to the power 9 nanometers. So meaning how many meters will be equal to 342 nanometers? This will just be 3.42 by 10 to the power negative 7 meters. So this is okay. Then if you work out this, what do you get if you divide these two? So make sure on punching you put these guys in brackets. That's the only way you will get the right thing. So put this in brackets and also put the down part in brackets. So what do you get? 1 point what? Joe, what are you getting? Second equation, our second equation is that energy is equal to the Planck's constant times what? Times frequency. So E simply means energy, which is always going to be measured in joules. Then your H is Planck's constant. This guy is a constant. So they will always give it to you. Yeah, this is something like a 6.63 times 10 to the power negative 34. This is joules seconds. So joules seconds, this is what you have. And your V, of course, is your frequency. Yeah, so your energy is in joules. This here is in per second. So now you already know that V was equal to what? Where there is V, we can put what? V was the same as, V we said is the same as C over lambda. So we can get this and replace here where there's V. I'm going to put C over lambda. This will simply be E is equal to HC over lambda. This creates a combination of the first equation and the second one here has created the third equation, which is this guy here. So this is our second equation. Then we have modified it to make it into that. So hope this is okay so far. Hope this is okay. Okay, silence means this. Okay, so if this is okay, we're just saying we can now write the other one. So the other one, before I even discuss the other equation, I want to talk about a certain portion that most people dislike. So there's a part that is called quantum numbers. So before I discuss the other two equations, let me just talk about this part here. So the orbital configuration that you learned in biology about using your orbitals. So I won't go back in details again because we did this already under atomic theory. We have 3 types of orbitals. By now you know. This can accommodate 2 electrons and the shape is a sphere. You know how this looks like. You know to say I have p orbitals. This can accommodate 6 electrons and they have a what? A dumbbell shaped, right? This is a dumbbell shape. And we have d orbitals. These can accommodate 10 electrons. Then they have a cloverleaf shape. We did this already under atomic theory in biology. Yeah, so this is the shape of the d orbital. Now, the main reason why they came up with this whole representation here this representation of writing your configuration in this manner is because, like we said again in biology, we said it tells us not only the ring or the shell where we are hanging out in, but it will also tell us the exact location, which is the orbital, and also the number of electrons involved in each case. So no wonder this representation is very nice. Now, this representation, if they give you a number in front, let's say there is an n, or rather let me say this, they write it like this. They say there's, let's say, 2s, then I put a 2 there. Or rather someone will get confused, so how about I say a 2p, then I put a 3 there. So this tells you the quantum number. This guy here is the principal called I'll talk about it later. This here tells you the orbital that you're dealing with. Then this tells you, so quantum just means shell, right? So we can just say, it tells us the shell, and this tells us the electrons that are involved. Electrons that are involved. So this is why we don't like the configuration from high school. For example, sodium, instead of writing this guy here, we'll just write using our previous formula here. We'll just put, we'll put 1s2, we'll put 2s2, we do 2p6, then you put your 3s1. This is better because it tells you to say in the first shell, you have 2 electrons that are found in the s orbital. In the second shell, this means second, right? You have 6 electrons in the p orbital and 2 electrons in the s. Then in the last shell, in the third shell, you have 1 electron in the in the s. Now, under quantum numbers, we have types of quantum numbers, and the first one that we're going to discuss is called, so this, let me just rewrite it here. So quantum numbers. So under quantum numbers, the first one that we'll discuss is called the principal quantum number. So Qn, I'll just denote this by Qn here. So principal quantum number. So what this tells us is the energy level that you're dealing with, the energy level. So it tells us the shell. Some people say it tells us the shell that you're dealing with. That's a principal quantum number. And these guys are denoted by letter n. They always start from 1, 2 until you reach positive infinity. That's what you have. Yeah, so like according to this formula here, the principal quantum number for this one here, the principal quantum number here is 1. Here it's a 2, right? This is the second shell. The principal quantum number here is what? Is 3. So you cannot have a 0 shell. It's either you have a shell or you don't have. No wonder. N always starts at 1, then it goes until you have positive infinity. This is what you have. Yeah, so if I was to give you to say you have n is equal to what? If I give you to say you have n is equal to 3, it means you're dealing with a third shell. So you need to know to say here you're dealing with a what? With a third shell. So hope this is okay. Hope this is not confusing. Hope this is okay. So the first type of quantum number, we just said principal quantum number. Though what it tells us the energy that we are dealing with, or the shell that you are dealing with. So that's basically what you have. Then the second type of quantum number is called the angular quantum number. So Qn. So this angular quantum number tells us the shape that we're dealing with. So this is going to tell us the shape that we're dealing with, and also or just the orbital that you're dealing with. What type of orbital are we dealing with? And also this can be always be gotten if you have this. So if you notice, the angular quantum number depends on the principal quantum number, because the angular quantum numbers range from 0 until you have n minus 1. N here is the principal quantum number that you were given. So if I give you to say, i.e., if n is equal to 3, meaning angular quantum numbers will be 0, 1 up to 3 minus 1 is what? Is 2. If I give you n is equal to 4, the angular quantum numbers will be 0, 1, 2, then 3. Is this okay, guys? Are you getting what we are saying here? So the angular quantum number depends on the principal quantum number. Yeah, so the range of the angular quantum number is from 0 until you have n minus 1. That's why you end. Yeah, so if I was to give you n minus, let's say 2, L will just be 0 and 1. That's all. If I give you n is equal to 1, because you know n can never be 0, because like we were given, n values start from 1 to positive infinity. Here L will just be equal to 0. So is this okay, guys? Is this okay? Okay, so this is angular. So you need to know what they mean. So principal, we say, tells us the energy, the shell we're dealing with. Angular tells us the orbital, the shape we're dealing with. Then the third one is called the magnetic quantum number. So magnetic quantum number. So this tells us the number of each orbital involved. Number of each orbital. That's what this guy tells us. So its domain is, or rather we symbolize this with a capital letter M with an adjacent, or rather a subscript letter L. So this is, some people would prefer writing it like this. If I may just write it like that, then you take a L here. This is always going to be from negative L, then 0, then up to your positive L. Some people will say this is the same as 0, then you have plus or minus 1 until you reach your plus or minus L. So notice that these guys are all related. Angular was depending on principal quantum number, right? Then magnetic is depending on angular. What is the L? The L is the angular quantum number that you are dealing with. So maybe if I may illustrate this, if I give you the principal quantum number to be n is equal to 3, you know to say the L values will be what? L values will be 0, 1 to 2. Is there anyone who is lost on where because we said L values range from where? From 0 until you have n minus 1, right? Our n is what? 3. So 3 minus 1, that's a 2. No wonder we're ending at 2. And you always just indicate whole numbers. Is everyone okay, guys, with n and L? Any questions on n and L? Is this okay? No questions? Okay, so if you're okay with the n and L, now we're going to use the L values that we've gotten to get the corresponding magnet, because we just have principal, right? This is principal here, principal we have, then here this is angular. Now how about magnetic quantum number? So we say we let L be equal to 0. What is ML going to be? Here we are supposed to have 0 and other things. We cannot have positive or minus 0, right? Remember the notation of ML is what? From negative L, we put 0, then we go to positive L, right? Now we're only given L to be 0, so we cannot go from negative 0 until we have positive 0 and then put a 0 there. This whole thing will just give us ML is equal to 0. So the first one here, when L is 0, ML is also 0. Then when L is equal to 1, ML will be negative 1. We start with the L, negative L. What comes next here is 1. What comes next is positive 1. Then if you have L is equal to 2, ML will simply be negative 2. Then we have negative 1, we have 0, then positive 1, until you reach positive L, which is positive what? Positive 2. Is this confusing, guys? Here, this is where people find it confusing. So please feel free to ask, guys, if this is confusing. So these will be the magnetic quantum numbers now that we're going to have. And we said these depend, or rather tell us about the number of orbitals. So when L is 0, it's an s orbital. Then when L is 1, these are p orbitals. When L is 2, these are d orbitals. When L is 3, those are f orbitals, and so on and so forth. So now we are just saying the magnetic quantum numbers will tell us the the number of each orbital that you have. So L is equal to 0 already tells us we have s orbitals. How many are they? There's only one. L is equal to 1 tells us we have p orbitals. How many are they? 1, 2, 3. So we have 3 p orbitals. The same applies here. When L is equal to this, we know we have d orbitals. How many are they? 1, 2, 3, 4, 5. So you see how we do this, guys, right? Is this okay? Yes, on the conversion, yes. Oh, it's okay. What you said is true, Christopher. It's like I just switched up things. Christopher, you know to say 1 kilometer is equal to 1,000 meters, right? So now, what about if I divide this side by 1,000 and I divide this side by 1,000, and I'll tell you to say 10 to the power negative 3 kilometers is equal to 1 meter. Is this still okay? Like this? It's exactly the same thing that happened there. So what I had written was that I think I wrote something. So either way, some people write this. This is nanometers. Or we can simply have 10 to the power negative 9 meters is the same as 1 nanometer. So whether you use the first one...
it's clear, so I never paid attention to the coefficient.
Oh,
the
yeah.
Power there.
Okay, yeah. So
now it's clear.
It's clear, okay?
Yes.
Okay, so we have done this part for quantum numbers. Now let me just give you a small example here. I just want to instill this thing in you. So if n is equal to 5, what will be our L values, guys? It will be 0, 1, 2. Where do we end on? What will be the last number for L?
4.
It will be 4, right? Exactly, correct. So for each L value now, we need to assign a magnetic quantum number. So when L is equal to 0, ML will simply be a 0. Then when L is equal to 1, ML will be, we write -1, then 0, then +1. Then when L is equal to 2, we simply assign this is -2. Then we know there should be a +2, right? So we assign everything in between, then +1. This, some people can just write this as 0, plus or minus 1, plus or minus 2. It's one and the same. This is the same as the sign. Yeah. Then the other one will simply be 3. So we have to go up to 3 and 4. So when our L, so we have this guy here, when our L is equal to 3, ML, you should be okay now if I say 0 plus or minus 1, plus or minus 2, plus or minus 3. Then the other one will simply be L is equal to 4. You know ML values will be 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. So this is what you'd get. You know these are F orbitals. How many are they? 1, 2, 3, 4, 5, 6, 7. There are 7 of them. These are G orbitals when L is 4. How many are they? 2, 4, 6, 8, 10. I mean 2, 4, 6, 8, then plus this, which is 9. So they are 9. Because it's just 1, then these are all 2, 2, 2, 2, 2, right? Yeah. So this is how we relate the 3 type of quantum numbers, but we still have a last one. The 4th type of quantum number is called magnetic spin quantum number. So magnetic spin, so this, say, magnetic spin is simply the main reason why we are going to be writing, this is represented by MS, M, we take a small letter s down. This is the main reason why we write electrons like your data symbol. We write them as one half arrow facing up, the other half arrow facing down, and this is spinning in this direction, the other one is spinning in the opposite direction. This is because we have to reduce the repulsions. Yeah. And the main reason, you notice each of the above quantum numbers, we were discussing their importance, right? But for spin, we just say these guys simply, the purpose of magnetic spin is to tell us the orientation of electrons in space. So the main reason why we have to know this is because we have to identify whether we can call a particular element to be magnetic or not. So there are two words that we'll be using. So the MS determines the magnetic spin quantum number is going to determine whether a particular element is called paramagnetic. So there are these two terms that we associate with this quantum number, or this is diamagnetic. So paramagnetic just means a lone pair, or rather let me say it's an odd number of electrons. Then diamagnetic meaning they are paired. This just means it's an even number of electrons. So to just cut this to straight to the point, I just mean like for sodium, if you write the configuration of sodium, sodium is going to be what? It's going to be 1s2, then you have 2s2, then you have 2p6, then you have what? 3s1. You look at the last thing, the last shell, or the last part that has been shown, the last thing is 3s1. Look at this. Focus on the number of electrons here. How many electrons are you having there? Only one. So if it's not paired, meaning if the number is odd, or it's a lone electron, meaning sodium is a paramagnetic what? Atom. Meaning it has magnetic properties because of the unpaired electron in the outermost shell. No wonder it loses fast. No wonder most metals are paramagnetic. No wonder they are easy to lose. They lose electrons fast. So these are the four types of quantum numbers that we have. So you need to know each one of them and their use. So magnetic spin just tells us whether your element is going to be paramagnetic or not. But the main reason is that it shows us the orientation of electrons in space, to say they're going to be facing in opposite directions. The main reason why they're facing in opposite directions is because they have to reduce repulsions, because electrons are negative. So we can't force two things that are both negative on one slot minus causing them to fight. So to minimize those repulsions and to accommodate them on a slot, we make them facing opposite directions. That's basically what we are saying. So after talking about this, now we can even discuss the fourth equation now. So the fourth equation is just here. We're just saying, remember how we said, so recall, I'll just say this, recall that energy is equal to the Planck's constant and that. Then we modified it again. We say this is the same as this. This is what we had because it came from this fact here. These are the three equations that we looked at, right? So since we've discussed that electrons are in a random motion, meaning they're able to move from one energy level to another, it means we should be able to calculate the energy in every particular shell. So there is a certain amount of energy that can be found in a shell. So there's a formula just that that is used, or rather applied. So this is just going to be the fourth formula, which is energy. Energy found in a particular shell is simply equal to, so this is given as, this sometimes can be fixed. So this will be given as negative 2.18 times 10 to the power 18 joules. This is 1 over n squared. So this is the energy, the formula for the energy level in a shell. Not all the shells have the same energy. As you move away from the nucleus, the energy increases. The bigger the number of the shell, so this is N1, the bigger the number, the more the energy. Reason being, we need more energy to convince an electron to continue staying in this last shell as compared to an electron which is closer to the nucleus, because the attraction between the protons, which are positive, and the electrons becomes weak as you move away from the center, right? So take for example someone who has commitments at church. So this part here, these guys here have commitments at church. It's rare for them to miss, right? Because they will be, it's noticeable for them to miss because they participate, they are close to the church activities. Someone who is just a church Sunday goer without any strings attached, any commitment, it's easy for them to just skip. They need more convincing for them to be in attendance as compared to someone who has involvements or commitments. So the more you move away from the nucleus, the more the energy that you have. Or in short, we're just saying the bigger the value of n. So n1 is less than n2, then this is less than n3, and so on and so forth. It just goes like that. So this here is our fourth formula. This formula here is used if you want to get the energy found in a particular shell. The reason why there's a negative is because these energies are always going to be lost. So they are exothermic processes. Note that there's a negative in front. So this is just for one particular shell. Then the fifth formula is when you're looking at a transition from one particular orbital to another. So the fifth formula is called the change in energy. The change in energy from one particular shell, let's call it N2, to another shell. So we're just saying we are coming from N1, then now you're going to N2. So let me use simple direct words here. I'll say final to initial, where you are coming from. So if you are moving from n is equal to 2, then you are going to n is equal to 5. This here is your initial. This is where you are coming from. Then this here is where you are going, right? That's your final. So we'll say the energy of the final place where you have landed minus the initial place where you were, where the electron was located. So this can be, since we know to say the energy in a shell, I'll call this n initial, is going to be negative 2.178 10 to the power 18. This is joules. This is 1 over initial. This is squared. Then the second one, so I'm trying to show you where the formula comes from, because there are two options of the formula that I'm going to give you. So this is this final. So if you want to find the difference here, so I'm going to let k be equal to 2.178, so that I have something short to write. This is 18 joules. So pali ponse palichi, I will just put k. So I just want to shorten my thing, so that when I write the change in energy, which is the energy in the final shell minus the energy in the initial cell, you should be okay if I say negative k, then 1 over energy final squared. This is minus, the other guy here is negative k, then you have 1 over initial squared. So you should be okay if I come down here and say this is the same as negative k, then you have 1 over this guy squared. This is simply a plus. There's a k, 1 over initial squared. I'm trying to make this into one uniform thing, so I'll write the positive one first. So k is common, and what you're having inside is negative 1 over this final squared, then plus 1 over this guy here initial. So this can be written as k is the same as the initial squared minus where we are going, final squared. So I've just switched these, just alternating them. So this will give you the first formula for the change in energy. If you're coming from any shell, 2.178 times 10 to the power 18 joules. If you're coming from any particular shell to another, you can use this formula to get your what? To get your energy. So this is what we mean by the change in energy. Other people will say the change in energy is equal to negative 2.178 when there's a negative in front, meaning they switched the things inside. Meaning here, instead of saying initial, meaning bayambana final hapa, squared, then minus initial, then squared. This is what you have. So please notice these formulas are just the same. The difference is in what you do inside. So if you here you start with initial squared, initial minus final, there will be a positive this side. If it's final minus initial, then there will be a negative in front. But either way, the answer you're going to get is always going to be the same. Nakamba maningi, guys. Are you getting what I'm saying? Macnon, are you following here?
Yes, I'm following.
So just showing you how we derive the formula, but you really don't have to know how we derive the formula. You just have to master this formula, either the first one, this one here that we're having, or you can be using the second one. So if I was to ask you to say, what is, let me give us a proper example here so that you see what we are discussing. Where does this apply, in case you're wondering, how do we use this formula? So example, an electron moves from, so I'll give us two questions in one, moves from n is equal to 2 and goes to n is equal to 3. So the first question is, find the energy that was involved. How much energy did it require? What is the energy change? In short, I'm asking for the change in energy. That's what we're asking for. Then the second thing that we're asking for is wavelength. Since you will know the energy, right, can you get the wavelength? So this is simply going to ask for the wavelength. So this will help us to get the, so here we're looking for wavelength. So you can just copy the question or just screenshot it, then okay. So if you're okay with you've copied the question, we can now start. So any initial where we are coming from is simply 2. This is the 2 guy that we have. Then n final where we are going to is simply 3. So I'll use the first equation which has a positive. So I'll say solution here. So solution, we're just saying the change in energy is going to be equal to, we have what, there is a 2.178, then by 10 to the power 18 joules. Then we said 1 over initial, right? Initial is 2 squared minus final is that. So this is going to be 2.178 by 10 to the power 18 joules. This is 1 over 4, then minus 1 over 9. So what do you get if you compute this? This is going to be 1 that. So this is Chem, guys. You're allowed to use your calculator. Just punch everything at once. That's going to be a 9 minus 4, which is a 5 over a 36. So what do you get if you punch this? What do you get? So let me just scroll down. I had paused it. I forgot to unpause the recording. So here we have the change in energy, which is here. Now we use the change in energy to get the wavelength using this formula. So this is the substitution we've done. So this is how we land on this part here. So what answer are you getting if you punch it? What are you getting, guys?
Yes, I'm getting 6.1.
1 what?
255. power 10 power
10 to the power what?
Times 10 power 9.
10 to the power 9. So this is 10 to the power 9. Now, this guy here is in meters. So we can just put it in a simpler number. This is supposed to be 0.13. You can just say this is the same as in nanometers, right? You can just cancel this. It's simply going to be that. So I'm just changing this because this is way too big. So this is the main reason why we prefer putting the wavelength in nanometers, because numbers in nanometers are very small. So we can have this guy. If I'm not mistaken, I'm saying 1 meter is equal to 10 to the power what? Is it? Am I doing the right thing? Yes. Yeah, so this is going to give us that. Any questions, guys, here? Is this okay? More about Christopher, is this okay?
Yes, sir, it's okay.
Okay. So aside from this, the last thing I should mention here before we end our class is the last concept under part 1 that you need to know is a concept that we call photoelectric effect. So photoelectric effect. So under photoelectric effect, we're just saying this is something known as the bouncing of light. So when you expose light energy to a metal surface, right? This is a metal. Let's say this is a metal here. When you expose light to this guy, let's say these are the rays of light to this guy, there's going to be a certain point. This is what we call a threshold. There is a limit. This is a limit to which the metal can continuously accommodate the light that you are exposing it to. At some point, it will start emitting off electrons. So electrons will be evaporating from the surface of the metal. So once that happens, this brings us to the last equation, which is simply the only equation where, so this is what we say, this is H. So this is the only equation where we say lambda is what? H mc, or lambda is equal to H, then we say mv. It's the only equation where v, this means velocity because it varies, because surfaces are different, so the speed that things are going to be moving with. So if speed is not given, you use what? You use c, which is the speed of light. Then if the speed is given, you use what? You use the same velocity that is given. And this is called, it has a name, it's called the de Broglie's equation. This is the de Broglie's equation. It's used to calculate the wavelength of any particular particle. So where the h is the Planck's constant, you know that already. This is a constant that is always given. This is Planck's constant. Then the mass is supposed to be in kilograms. This guy here is the mass. It has to be in kgs. Then v and c mean the same thing. This means the speed, or rather the velocity. And this is important because the next part that we are going to look at is about the spectrum. So the prism, those things, the spectrum thing, the colors and everything else. So this will usher us to discuss the next part. But please take note, our 60th equation is having a name. Whenever something has a name, just know that it's special. This is the de Broglie's equation. It can be used to calculate the wavelength of any particle, provided we know the velocity and the mass that it is moving with. So this is the last part that we're going to look at today. So we'll cut the class, we'll end the class here, unless if there are any questions. So we'll continue from here now with part 2 of the topic. Any questions, guys, here?